Today is the 16th episode of Nodutalk. Our today's speakers, Mr. Staff Hendricks and Dr. Basutkar, will share the key process controls and best practices to help you to achieve consistent magnesium recovery, minimize the treatment variation, and improve the product quality. Over to you, Mr. Staff Hendricks.
This evening, we are going to several important items of the process that's known as the nodularisation, or one of the metallurgical treatments, which is nodularisation and inoculation. The target of the foundry is producing a casting with the correct properties at the lowest cost. This can be by applying process control. A process every one of us has, because the process is a number of activities you do one after another, but the control is very, very important to get the best result. Defects and inconsistency is due to an incorrect process control. Never forget that. If the process is controlled properly, there will be consistency and there will be less to no defects. The process for nodulising is, first we have to talk about the liquid metal in the furnace, then the metallurgical treatment, that's nodulising and inoculation, then the cleaning of the treated metal, the transport to the mold, the cleaning of the liquid metal at the area of the mold, and then pouring and the second inoculation. That's the complete process of a metallurgical treatment. In the furnace, what is important? First, the chemistry, of course. Every one of us knows that you must have chemistry that you have to target to get the proper, let's say, matrix, ferritic, paralytic, ferritopalytic, and so on. The temperature and its history is another very, very important factor and is many times forgotten. The third one is the metallurgical quality, and that's a good nuclei giving a better structure and stronger casting. These three we will discuss further. The chemistry. First is the carbon equivalent. Second is the sulfur content. Third is the elements that degenerate free graphite and make intercellular graphite. And fourth is the elements that form carbides. Here we see at the left side the carbon equivalent. It's of course the balance between carbon and silicon. We have a preferred range, as we can see in the graph at the right side, and if we are outside of the green area, some problem will occur. It's not a matter of can occur, some problem will occur. If we are above top red line, we will have graphite flotation. If we have in the let's say in the top of the triangle low impact, we will have left of the bottom red line, we will have excessive shrinkage, and if we are under the 2% of silicon, we have a tendency to form white iron. Always when you have your carbon and silicon, please check it in this graph. The sulfur content. The sulfur content decides about the amount of magnesium to be added to form magnesium sulfur. The maximum sulfur content before nodulising is 0.025. If it's higher, we have to do a pre-desulfurization because only compensating a higher sulfur content with magnesium is much too costly and will lead to much too slack, which will be nearly impossible to remove. What we will have to do for that, use the proper pig iron, the proper carburizer, and ferromanganese if you add it, because in these three, the sulfur content can be too high. Elements that degenerate free graphite. Besides sulfur, there are a lot of other elements that promote degenerated and intercellular graphite. We have seen it in previous lectures, but I want to repeat it because it's mostly forgotten by a lot of foundries, also in Europe. The degenerated elements are titanium, lead, tin, bismuth, please read very carefully, bismuth, antimony, arsenicum, and aluminium. And the elements that promote intercellular graphite, if they have a wrong content, is copper, titanium, tin, bismuth, antimonium, arsenicum, cadmium, zinc, and zirconium. So to know if this degeneration or intercellular graphite is playing, you have to analyze your liquid metal to see if they are present or not. Elements that form carbides, manganese, and luckily every one of us knows that the manganese in ductile iron should be never more than 0.40%, and in ferritic never more than 0.20%, so that carbide formation of manganese will be less. But titanium can form it, chromium can form it, vanadium can form it, and also molybdenum. And there are some types of ductile iron, the silicon molybdenum ductile iron, that have a big problem with the formation of molybdenum carbide. You see in the bottom that the carbides can also become from manganese. If the manganese content, especially the free manganese content, is too high, you will find matrix picture like this with a lot of manganese carbides. The temperature, and this is many times forgotten that it's a very important element. The temperature has an influence on the amount of magnesium to be added to neutralize the sulfur and the oxygen, because we can see it in the formula for nodulizing. We will come later back on that the temperature is also involved there. It's important to realize that the formation presence of nuclei is depending on the temperature history of the liquid metal. On the right side, you can see it. If the temperature is below the Tg temperature, SiO2 is formed. SiO2 are the nuclei you cannot miss. They must be in the metal. So if you go above Tc temperature, the loss of SiO2 is very important, and you will also lose carbon. This is a process, so it's not only the temperature, but also the time on the temperature. If you are very short above Tc, very few will happen. If you are a long time above Tc, you will lose a lot of nuclei, and your quality of your liquid metal will be very low. How can you see the metallurgical quality of your iron? Yeah, you have the thermal analysis equipment where the cooling curve will tell you a lot. We will see that if you have a too high delta T or R recalcitrance mainly, then you will have to do something, because the number of nuclei is not sufficient in your liquid metal, and you will have to do a pre-treatment in the furnace that can be done by pig iron or a preconditioner alloy. The inoculation will increase the nuclei after nodulizing. Please don't count only on inoculation. Before you start with the nodulizing and tapping the metal, make sure that your recalcitrance, at what I always did during my whole career, that the recalcitrance was 3 degrees or less. If it was more, I did some extra things like pig iron, preconditioner, and so on. If it was more than 7 degrees, then I did not use that iron anymore, because it was nearly impossible to restore the quality of that liquid metal.
In the metallurgical treatment, can you hear me now?
Yes.
In the metallurgical treatment, what are we looking for? We are looking for having a nodularity in the casting of more than 85%. We don't want any degenerated graphite, free graphite in our structure. And we want to avoid magnesium carbides in the structure. Good nodularizing produces HgIron, high nodularity and clean metal. And after the nodularizing is over, we add the inoculation. The idea is to increase the number of nodules and to produce a homogeneous matrix structure. Good inoculation ensures more nodules and a homogeneous matrix for consistent properties. In metallurgical treatment, nodularizing, first is required to calculate the required magnesium according to the formula. Then we have to check the required amount of rare earths present in our metal and in our magnesium treatment alloy. We have to check if too much free magnesium is present, it can cause carbides in our casting structure. Follow these steps for successful nodularizing and high quality castings. The metallurgical treatment of nodularizing is worked out from this formula. The weight of the ferrosilicon magnesium required is equal to the weight of the metal in the ladle multiplied by the percentage magnesium residual required in the final casting plus the amount of magnesium tied up between the initial sulfur and the final sulfur and the time which is spent after the magnesium treatment and before pouring and solidification of the metal. This is divided by the ferrosilicon content of the magnesium in the magnesium ferrosilicon alloy, the magnesium content in the ferrosilicon alloy, and the efficiency of the process. Capital T is the actual temperature at nodularizing, and 1450 is the TG graphite temperature, which Staff just explained to you, where we form up to this temperature lot of nuclei. So this is the general formula for working out the amount of nodule magnesium ferrosilicon required to get a nodularity of more than 85%. A nodularity of more than 85% can be obtained if the violent reaction does decrease the efficiency. If the reaction is too violent, it decreases the efficiency of magnesium treatment. The efficiency of the magnesium treatment is lower if there is a higher content of magnesium in the alloy. The efficiency of the magnesium treatment is lower if there is more oxygen in the metal. So violent reaction, higher magnesium content, and more oxygen in the metal will lower the efficiency of the magnesium treatment reaction. The factor of 10 raised to minus 3 into time is a factor which accounts for the fading of the magnesium after treatment. If you spend more time after magnesium treatment, the loss of magnesium from the metal will be more. Depending on the covering of the treated metal, liquid metal, this loss is around 0.001 to 0.0015% per minute of holding the metal. So after the magnesium treatment is over, we have to act fast to dispose of the metal into the mold. The reference temperature of 1450 is chosen because it is mostly around the TG temperature below the formation of SiO2 is done. And above the TC temperature, the magnesium reaction is more or less violent and magnesium oxide will be formed easier. So we have to ensure that our temperature is very, very well controlled and measured every time, every treatment. It's not okay just to have the treatment temperature but not measure it to control it. This is one of the most important process parameters for the magnesium treatment. The factor of 0.76 multiplied by the difference in the initial sulfur and the final sulfur is about the free magnesium content. Magnesium reacts with sulfur to form magnesium sulfide. Therefore, the presence of 0.76 into sulfur gives you the amount of magnesium which is tied up with the presence of sulfur in the metal. And the rest is the free magnesium which is required. The free magnesium which is required is actually equal to the magnesium indicated by the spectrometer analysis minus 0.76 times the sulfur indicated by the spectrometer analysis. The spectral report, which indicates the magnesium content and the sulfur content, should be used to determine how much is the free magnesium in our metal after magnesium treatment. The free magnesium is required to know because that controls the nodularity of the graphite. So free magnesium is magnesium specified by the spectrometer treatment minus the magnesium tied up by the amount of sulfur represented in the report of the spectrometer. Control sulfur level to ensure sufficient free magnesium and achieve the required nodularity of 85% and above. We should not have any degenerate free graphite in our structure. The main purpose of rare earth is to immunize the free graphite degenerating effects. The formula is the rare earths which are required to neutralize the effect of these bad elements are titanium, antimony, lead, bismuth, and tellurium. So the formula for the amount of rare earths required to neutralize these elements is given here. Titanium divided by 5 plus antimony divided by 0.5 and lead divided by 0.5 plus bismuth divided by 2 plus tellurium divided by 0.5. The rare earth should be more than this to be present to be ensuring that there is no free degenerated graphite in our structure. If cerium and or lanthanum is too high, chunky graphite will appear in the microstructure. This appearance depends on the wall. Yes, Staff, we can hear you now. Would you like to take over? If cerium and or lanthanum is too high, this appearance depends also on the wall thickness and the amount of silicon, nickel, and calcium in the metal.
I will repeat then about the degenerated free graphite. We see the formula there of the cerium you need to compensate the elements who are titanium, antimonium, lead, bismuth, and tellurium. And if the cerium and or the lantanium, because they are similar, is too high, chunky graphite will appear, especially in thick sections. The appearance depends on the wall thickness, but also on the amount of silicon, nickel, and calcium. The more silicon there is, the higher the risk is. So if we see the new types of ductile iron from the EN standard with a higher silicon, about 3% and more, pay attention, because their chunky graphite is very, very quickly appearing. Here again, I give a recommendation that I use about the cerium, that should be cerium from the spectrometer minus the others compensated elements. You can see that the cerium active should be maximum 0.015 to 0.02 for minus 25 millimeters thickness. If you go to a 250 millimeter, it's preferred to have no free cerium, and definitely even no cerium at all. That's the much better for the very thick sections.
Dr. Basutkar, can you continue?
Yeah.
Because he's having some
If
audio
you,
problem.
if you want no degenerated graphite in the structure, there is a relationship between the magnesium and the cerium content for getting the proper free graphite. On the y-axis, you see the rare earth content, and on the y-axis, you see the magnesium content, and on the x-axis, you see the rare earth content, the Re content. At the very low level of rare earths and residual magnesium, you have flake graphite. The higher the residual magnesium increases and the rare earth increases, we have compacted graphite. Little higher than that, we have nodular graphite and compacted graphite. We don't want to avoid the formation.
Next slide, please.
So let's start with this slide once again. This slide indicates what are the conditions under which no free degenerated graphite should be present in the structure. In the graph below, we have on the left-hand side the percentage residual magnesium, and on the bottom, on the x-axis, we have the percentage of rare earths in the metal. Can we go back to the old? Yeah. So this slide indicates the preferred range of ductile iron production with no free degenerated graphite. So we have to work in this light blue area and avoid this dark blue, light green, and purple areas. These are the no-no areas. The best area to operate is heavy section, medium section, and thin section is the light blue areas shown in this graph. How to avoid magnesium carbides? If there is too much of free magnesium, carbides can be formed. In this graph, we have to work in the green area. On the y-axis, you see the percentage sulfur indicated by the spectrometer, and on the x-axis, you see percentage magnesium indicated by the spectrometer. We always need to work on the green area. If you are on the left-hand side of the green area, you will have low nodularity, and if you are on the right-hand side of the green area, you end up with carbides, low nodule count, and shrinkage in the casting. So the best range to operate with your magnesium and sulfur is a green area. Concerning the type of treatment, the efficiency of the magnesium treatment depends upon the type of method you use for magnesium treatment. The three well-known methods are the sandwich type treatment, the tundish covered ladle treatment, and the magnesium wire treatment. Each of them has advantages and disadvantages. The treatment ladle should have height to diameter ratio of more than 2. So the efficiency of the treatment depends upon the treatment method used. The sandwich type, the tundish cover ladle treatment, and the magnesium wire treatment. Let's go to each one of them and the requirements. The sandwich type treatment, the method is the easiest and less costly, but it depends a lot on the pocket shape and size. First part of tapping should be very quickly to fill the ladle and to be away from the magnesium pocket. It should be in the other half, and it also depends on the type of ferrosilicon magnesium rare earths. First metal will flow here. You must avoid the first metal polymer covering material of the magnesium alloy. The thin steel chips, plates, or special design ferrosilicon serves as inoculant. Quantity 0.5 to 1%. Treatment alloy at the bottom is ferrosilicon magnesium with rare earths. Pocket must contain both the ferrosilicon magnesium and the cover material used to cover this alloy. So there should be enough room in the pocket to put the magnesium alloy, the inoculant, and the cover material. And when you are tapping the metal should be away from this combination. It should fall in the other half of the ladle where there is no magnesium and cover metal. This is clear. Let's talk about the sandwich method. It depends a lot on the pocket shape and size. The pocket must contain all the ferrosilicon magnesium with rare earth and have enough room for another cover material that will be put, normally 1 to 2% on the top of this ferrosilicon magnesium and probably with ferrosilicon inoculant. The cover must be thin steel chips or plates or specially designed ferrosilicon, which also serves as an inoculation. The quantity of this ferrosilicon is mostly between 0.5 to 1% of the metal weight. The first metal may never hit the pocket area to avoid early reaction of the treatment alloy. So it's very important to ensure that the first metal tap is away from the magnesium alloy and the cover. It has the lowest efficiency for the magnesium and depends a lot on the operators and the training. Lose a lot of magnesium treatment, higher tapping temperature required for this method. This is a disadvantage of this process. In a tundish cover ladle method, this is a more costly type of treatment. Investment is involved and maintenance of the ladle cover, but usable for different types of alloys as far as magnesium and the rare earths are concerned. It gives you higher efficiency concerning magnesium due to higher pressure inside the ladle. Therefore, there's less vaporization loss of magnesium. It is less dependent on the operator's training, and nearly no fumes are seen in the working area. No magnesium fumes are seen in the working area. This is a very nice process, unfortunately a little expensive, but it gives you very consistent magnesium recoveries. Tundish cover ladle treatment is an investment. It gives higher magnesium efficiency, less operator dependency, and nearly no fumes, magnesium fumes in the working area. It's a good process to consider. Tundish cover ladle, the pocket size is critical. This should contain all the ferrosilicon magnesium and have plenty of room for covering material. The covering material should be thin steel chips, plates, or specially designed ferrosilicon, which serve also as inoculation. Easy to use different treatment alloys concerning rare earths. You can use rare earths of different Re content in this method. It has the highest efficiency for magnesium and is nearly not depends on the operator experience. There is very little loss of magnesium metal treatment in this method. Pocket size is critical. Covering metal should be thin slips, chips or plates. Easy to use different magnesium treatment alloys and of rare earth content. Has the highest efficiency for magnesium and is nearly not depending on the operators, and less loss of metal temperature. This is the most important instrument, process control parameter that we can control by this method. Wire treatment is most costly concerning equipment and treatment area. You require a machine to feed the wire into the ladle. This is not depending on the operator unless the setting is incorrect for wire speed or incorrect weight of the metal in the ladle. Use of high magnesium content wire. More than 50% magnesium containing wire is used. So the losses of magnesium is more in this treatment. Wire treatment is very violent reaction. It depends on the magnesium content of the wire. It produces a lot of slag. High loss of metal temperature. Restricted concerning ladle size diameter. Difficulty to use different types of magnesium combined with rare earth additions. Needs more inoculation due to loss of nuclei. These are the disadvantages of the magnesium treatment using a magnesium wire method. Concerning the types of magnesium treatment, these are the rules for nodularizing using the treatment you want to use. Open ladle or sandwich method, typical recovery of magnesium from the alloy 30 to 35%. Required magnesium ferrosilicon addition 1.8 to 2%. Relative cost, alloy cost is highest for this treatment. In sandwich method, pocket 40 to 50% is the magnesium recovery typical. Required ferrosilicon magnesium 1.4 to 1.6%. And relative alloy cost is moderate. Tundish cover ladle, typical magnesium recovery is about 55 to 65%. Amount of ferrosilicon magnesium addition required 0.9 to 1.2%, and relative alloy cost is low. Cold wired injection treatment, magnesium wire, the typical recovery is 60 to 70%, is optimized dynamically, and the relative cost is lower. Rules for nodularizing, concerning type of ferrosilicon magnesium addition. For the ferrosilicon magnesium alloy to be selected, you must know the magnesium content depending upon the type of method you are using for magnesium treatment. You must know the rare earth content depending upon the subversive elements which are present in your metal. You must know the calcium content because calcium will affect the addition requirement of the ferrosilicon magnesium. Calcium is a very, very, very strong oxide and sulfide former. Key takeaways are correct balance of magnesium rare earths and calcium is essential for stable SGN quality. Right levels, right timing, right pocket design, and right operator practice. This gives you consistent results. These are process control requirements that you must keep in mind when using the ferrosilicon magnesium nodularizing treatment. No magnesium content higher than the magnesium content leads to more violence of reaction. If there is high magnesium content, it leads to violence of the reaction. It leads to more slag formation, and it leads to higher loss of metal temperature. So high magnesium is not desired to be present in the alloy. It leads to higher magnesium content, leads to more violence of the magnesium reaction, leads to more slag formation, and leads to higher loss of metal temperature. In-mold treatment needs much lower magnesium content, 1 to 2%. The silicon content in the base iron is highly restricted for the in-mold treatment. For sandwich and dish cover methods, mostly 4 to 6% magnesium containing alloy is desirable. Some people also use 6 to 8%. 6 to 8% magnesium containing alloy required where you have to control the silicon. Otherwise, 4 to 6% is ideal alloy to be used for sandwich and the condition cover method. Wire, the magnesium content is very high, more than 50% magnesium. Base iron can have a high sulfur content. We can look at both number 2 for sandwich and condition and for wire inoculation. If you have to control the silicon content, you have to keep the magnesium in the alloy less. If you have to have less control on the silicon metal, then you can use higher magnesium containing alloy for the sandwich and condition method, and you can use high magnesium alloy for the wire inoculation. The addition of rare earth depends on the presence of degenerating elements, as we have seen, and must be adapted to the real presence, not based on guesswork. Independent from the magnesium addition, which is only depends on the sulfur content. Most people determine the magnesium addition based on the sulfur content, but they do not take into account the real presence of the independent alloys, which can have a bad effect on the formation of degenerated free graphite. Too much rare earths will lead to chunky graphite, especially if the casting wall thickness is thick, if there is presence of higher silicon content, like in the SSS alloys, or if there is presence of higher nickel content. So keep in mind that too much rare earths will lead to chunky graphite if the wall thickness of the casting is high, if there is too much of silicon present, and there is presence of nickel in the compensating a too high rare content with antimony addition cost twice. First, addition of rare earth, and then addition of antimony. Antimony has also a strong product promoting effect. So antimony needs rare earth. So first you have to have a cost of adding rare earth, and then if you want to add the antimony addition, you have to cost the adding rare earth to neutralize the effect of antimony on the degeneration of graphite. Analyze and know the real presence of degenerating elements. This is often overlooked in the foundry. They take a general value and add rare earths depending upon the presence of these elements. Add rare earths only as per requirements, not by assumption. Maintain optimal RE levels for the nodular graphite. Avoid over addition to prevent chunky graphite and extra cost. Right RE addition is equal to better quality and lower cost. Key takeaways: add rare earths based on real need to counter generating elements. This is often a neglected parameter in the magnesium treatment process. Too much rare earth causes chunky graphite, and compensating with antimony costs more because antimony will increase the formation of pearlite and also requires additional rare earths to avoid the formation of degenerated graphite. The calcium content, effect of calcium content. Calcium does not dissolve in the metal. It has got highest free energy of formation. Calcium and barium form oxides, sulfides, and iron and tin have got the lowest energy of formation of oxide. Calcium initiates liquid slag. Using too much of calcium initiates a lot of slag buildup in the metal. Calcium is more aggressive to sulfur and oxygen compared to magnesium and rare earths. If calcium is present, less magnesium is required because calcium reacts with the sulfur and oxygen, and that much of magnesium is not required to be added because magnesium is job in the absence of calcium is to combine with sulfur and oxygen. If calcium is present, this takes away a part of magnesium's effect, and therefore you require less magnesium, which we are using calcium in the alloy. Calcium also makes the magnesium treatment alloy less violent. So some people use high calcium to subdue the violence of the magnesium treatment alloy. Rules for nodularizing. Process parameters and its effects. Why do foundries consume more ferrosilicon magnesium than necessary? Sulfur before treatment. As indicated earlier by staff, the sulfur before magnesium treatment should be less than 0.025. Ideal would be to have 0.014 to 0.016 sulfur. If the sulfur in the initial metal before treatment is more than 0.025, it is required to do the pre-desulfurization and get a sulfur below 0.025 before doing the magnesium treatment. Treatment temperature. If the treatment temperature is too high, you lose magnesium by evaporation. Normally, the ideal temperature of treatment should be between 1480 and 1520, depending upon the weight and the how the temperature has been raised. Higher metal temperatures, higher magnesium losses. Treatment method. There's a variation between the treatment method depending upon open magnesium treatment method, sandwich method, conditioned method, or magnesium wire method. Open treatment method is the least recovery. Conditioned ladle is the best method for magnesium recovery. Treatment time. Longer treatment leads to fading. Treatment time should be as low as possible, depends upon how fast to fill up the metal and cover the magnesium alloy and the cover metal. If the treatment ladle is filled up with the liquid metal more than half the height of the treatment ladle, then the reaction will be delayed and the recovery of the metal will be magnesium will be faster. So fast falling of the metal in the ladle is important. And once the reaction starts, it may be a good idea to stop pouring the metal from the furnace into the ladle. Let the magnesium reaction be over, because when the magnesium reaction is taking place, the weight of the scale showing the weight of the metal is not stable, and you are not able to judge how much metal you are tapping from the furnace into the ladle. So let the magnesium reaction get over, and then you tap the rest of the metal from the furnace to get the exact metal that you wanted to treat from the furnace. If there's only one hit to be tapped, this is not important because you'll be emptying out the whole furnace. But if there are more than one treatment to be taken, then you must control the amount of metal tapped from the furnace depending upon when the reaction starts. Stop tapping the metal when the reaction starts and top it up when the reaction is over and the scale is stable. Treatment time. Longer treatment time leads to magnesium fading. Cover steel. It prevents magnesium loss. Alloy particle size. Mostly in the foundry, people have only one or two alloy sizes, particle sizes. But they use different magnesium treatment for casting of different wall thicknesses. So you need alloys depending upon the magnesium treatment weight and also depending upon the type of casting you're making. Oxidation. The slower you pour the metal, the more oxidation takes place and there is more alloy loss, magnesium loss during the oxidation of magnesium with the oxygen. Pouring delay. After the magnesium treatment, if there's pouring delay, you are losing magnesium by fading. So once the magnesium treatment is over, you have to work very fast to avoid the magnesium fading losses and do all the activities of the magnesium treatment as soon as possible. Slag formation. When in slag formation, it traps magnesium. And magnesium trapping means you're losing magnesium from the metal. So please consider these process parameters which are undertaking the magnesium treatment. Make sure that your staff knows the effects of the elements on the magnesium treatment recovery. How to decrease the cost of nodularizing? Never reduce alloy blindly. Instead, improve the process efficiency. What are some of the potential actions that can be taken to improve the process efficiency. Lower sulfur in the base iron. Base iron sulfur, if it is between 0.014 and 0.016, that's the best. But it should be in any case less than 0.025. If it is more than 0.025, please do desulfurizing prior to magnesium treatment first. Next, improve the magnesium recovery by type of treatment and proper execution of the treatment. Minimize fading by the time of adding the metal, the temperature of the metal, and avoid or lessen the contact of the metal with the air. More the contact, more the oxidation, loss of magnesium. Reduce the oxidation. Your charged material should not be rusty. They should be rust-free. No dirt during melting. Tapping and pouring at low height to avoid contact with the air. Distance, ladle and furnace, and distance between the ladle and the mold. This should be as low as possible. Reduce slag if possible, but remove slag completely. First, try to reduce slag. Keep the sulfur low, 0.14, 0.16, and remove slag if the sulfur is more by removing the slag as much as possible. Remove all the slag. Optimize inoculation. Maintain pouring discipline. Fill the molds fast and make sure the metal is seen in the pouring basin as soon as possible. Monitor residual magnesium regularly after treatment, just before pouring in the casting molds. How to decrease the cost of nodularizing? Let us start from the top. Low sulfur. Often sulfur should be required between 0.14 and 0.16%. Ensures maximum magnesium recovery. Then go down on the left-hand side. Consistent alloy. Use consistent quality of ferrosilicon magnesium alloy with control size of the grains. Low slag. Less slag formation, more magnesium available, and cleaner is the melt. Good inoculation. Proper inoculation for nodule count and nodularity. Fast pouring on the mold. Pouring immediately after the treatment to minimize the magnesium fade. Come back to the top. Low sulfur on the right-hand side. High magnesium recovery. More magnesium recovered, less is the alloy required. Controlled temperature. Optimum treatment temperature 1500 plus minus 20 degrees. Proper ladle. Correct design of the ladle. Height to diameter ratio of more than 2. Good lining. And the most important thing is to keep the insulation material between the outside metal shell and the inside refractory. Most people in the treatment ladle do not use a proper insulation, and there is a lot of temperature loss. If you put asbestos millboard or put the thermal blanket between the steel cover outside of shell of the ladle and the refractory inside, you will be able to prevent loss of heat loss by radiation. And this is a good way to protect and keep your temperatures of the metal high, then to increase the temperature of the metal in the furnaces to compensate for the metal temperature losses. Low oxidation. The furnaces should always be kept covered when the metal has been prepared. Don't keep the furnace lid open, otherwise the metal from the top is getting oxidized very badly. The result, lower magnesium ferrosilicon consumption, stable nodularity, and lower casting cost. So what are the comprehensive cost reducing roadmap? Action. Convert from open ladle or sandwich method to tundish cover method. What are the financial benefits? Cuts ferrosilicon magnesium consumption of almost 30%. Metallurgical impact drastically lowers the dross and air exposure. Priority level, this is the highest priority for highest return on investment. Drop base sulfur to less than 0.012. 0.014 to 0.016 what I recommend. After magnesium treatment, it should be less than 0.012. Normally between 0.10 and 0.12. It eliminates wasted magnesium to sulfur reactions. It reduces slag inclusion defects. Low capital cost. The priority for this is high as it involves low capital cost. Lower tap temperature by 25 degrees. Saves furnace energy, slows magnesium fade. It extends ladle refractory life. It's a high priority material. There's a process change involved. Shifts silicon to late stream inoculation. Swaps expensive ferrosilicon magnesium carrier for base ferrosilicon. Increases nodule counts in thin walls. And medium priority, process variable troubleshooting. First, by looking at the symptoms at every treatment, you can take the corrective action, which are after you fix up the likely causes. Early flare, which means low recovery of magnesium. The likely causes cover layer too thin or wet or tap stream hitting the pocket directly. If the reaction starts too early, look for these process variations. Corrective action is increase the strap cover weight, aim the tap stream away from the pocket. In some of the old foundries, maybe 50 years back, people used to cover the ferrosilicon magnesium resin bonded shell sand. When you did this, you could fill up the whole ladle without the magnesium reaction starting. And then when the full ladle amount of magnesium to be treated metal is delivered into the treatment ladle, you take an iron rod and you puncture the steel shell, steel cover shell, and the reaction starts. And the recovery is to be very, very, very high, close to 60%, 62%. Other symptoms, late or weak reaction. Alloy size is too large, or ladle pocket is too deep or cold. This brings us to the temperature of the treatment ladle before magnesium treatment. The treatment ladle should be as hot as possible. Temperature of the lining more than 1000 degrees or closer to 1200 degrees. Use smaller alloy grains. Ensure ladle is thoroughly preheated. I just mentioned the ladle lining temperature should be approximately 1000 to 1200 degrees. When preheating the ladle, keep the ladle upside down so the ladle heater is from underneath the ladle and not from the top of the ladle. If you're using a top ladle heater, most of the preheating ladle flame is lost to the air. So you have to cover it. Best is to keep the ladle horizontal or keep it upside down. Erratic magnesium levels between the shifts. In between the shifts, you are required to have different magnesium levels. Then mostly it is a human error in weighing or pocket preparation. Automate ladle weighing system. Create a visual SOP sublist for optimization. This is a golden rule. The cheaper ferrosilicon magnesium rare earth is not the one you purchase at the lower price. It is the one that gives the highest magnesium recovery for your process. Treatment, magnesium treatment, nodulising and inoculation. Inoculation, idea is to increase the number of nodules and to homogenize the matrix structure. Process control steps to maximize magnesium treatment efficiency. 1. Liquid metal in the furnace. Don't neglect the liquid metal in the furnace. Its temperature, it's covering the furnace, making sure the temperature is taken just before tapping. Don't overheat the metal. Keep the metal below the TC temperature. The temperature should be close to TG temperature. Metallurgical treatment and nodularising inoculation. Cleaning the treated metal. First in the furnace, next in the treatment ladle, third before pouring the molds, cleaning the treated metal of the slag. Mold transport to the molds. Treatment ladle transport to the mold. Once the magnesium treatment is over and the metal is cleaned, transport the treatment ladle as fast as possible to the molding area. Clean the liquid metal. Before pouring the molds, clean the liquid metal of any slag. And last, pouring and secondary inoculation required to increase the nodule count. These are the parameters which should be considered before the magnesium treatment. So the next two processes of nodularizing and metal pouring are controlled very efficiently to reduce the cost of treatment and to increase the efficiency of the magnesium treatment.
Thank you, Dr. Basutkar and Mr. Staff, for covering the today's topic. It was a very good information.
This session was very informative, and we are also producing the SJ iron in our company. For the improvement of the process control, whatever the suggestions you have given, we are following that almost. The only thing is, we wanted to know what is the ideal CE, carbon equivalent, to improve the process or improve the metallurgical qualities in the castings.
The carbon equivalent required, it depends upon that graph which as staff showed you. Two red lines on the top. If the carbon equivalent is too high, you have graphite flotation. At the bottom, if the carbon equivalent is too low, you have got low impact. On the left-hand side, if the carbon equivalent is too low, you have got shrinkage. On the right-hand side, you have got explosive graphite. And the best guideline for selecting the carbon equivalent, according to me, is to use the table provided by Rio Tinto Mr. Kaban, in which he has given the different wall thickness levels of the castings from less than 12 millimeters in 12 to 25 millimeters, 25 to 50 millimeters, 50 to 100 millimeters, and more than 150 millimeters. For different wall thickness sizes, he has given the carbon equivalent, he has given the ranges of silicon, phosphorus, magnesium, and nickel, and tells you what should be the carbon equivalent in your casting depending upon the wall thickness. I do not know if I've answered the question, but I would very strongly recommend that you refer to that table to select the carbon equivalent based on the wall thickness of the casting for which you are preparing the liquid metal.
Yes, I have heard it. I completely agree, Mr. Bazutkar, and I use always the graph. And let's say the green zone is the one you should be in, whatever. With smaller, thinner castings, you can go a little bit over 4.4, but not that much. Even with big castings, don't go under 4.3. It's a good 4.3 to 4.4. Carbon equivalent should be very good, and check it then with these graphs, who will give you more security that it's okay.
Coming to the tapping temperature, sir, you are recommending that the tapping temperature should be 1450 to get the good results on the recovery of the magnesium. Hello?
Okay.
Yeah.
Okay, shall I answer?
Yeah, please.
I will complete first. I will complete.
Okay.
Okay. The tapping temperature, you see, the tapping temperature is depend upon directly with the pouring temperature. If the pouring temperature is 1390 to 1410, and including the tapping time, deslagging time, and traveling time with the ladle, treated metal pouring into the pouring ladle, all it matters, no, sir?
Yes, it does.
So that then accordingly, to maintain my pouring temperature, I require to keep my tapping temperature in the furnace, considering all the losses in the process.
You have answered your own question.
How myself I will restrict to 1450? That is one question, sir.
No, I didn't say we should have 1450. In very large ladles, which contain 15 and 20 tons of liquid metal to be treated with magnesium, the tapping temperature is about 1400 to 1420 because there's hardly any temperature loss. But the most important thing which you have probably not covered is the temperature loss during the magnesium treatment. People want to keep the magnesium pouring temperature same, and to avoid to get the required pouring temperature, they unnecessarily increase the metal temperature in the furnace to compensate for the metal losses. I gave you one example of how to avoid the metal loss in the magnesium treatment ladle. You must insulate the ladle lining from the steel cover by some kind of asbestos or thermal blanket to keep the temperature loss low. Keep the cover on the ladle, keep the cover on the furnace. There is no point in increasing the temperature of the metal in the furnace just to compensate for the temperature losses. You should reduce the temperature losses as much as possible and increase the rate of transporting the metal, pouring the metal, covering the metal, deslagging process. Avoid the losses as much as possible instead of increasing the metal temperature to compensate for the metal losses. This is my comment, staff.
Yeah, I agree, and I have to add something, and that is, please, the tundish cover treatment ladle is the one who gives the lowest loss of temperature. That's the first. Secondly, I see sometimes foundries and the distance between the furnace and the ladle is very, very, very big. And in the beginning, when you start tapping, there is a very small amount of metal coming in contact with the air. It will decrease a lot. And during the transport, please cover the ladle with whatever, a blanket or whatever you do. Cover the ladle and pouring the spout of the ladle as close as possible to the pouring, to the mold, to the pouring box. I many times have, and now I talk about India, could decrease and let's say the tapping temperature by 30-40 degrees C. Many times, but you have to consequently follow the rules.
Okay. Then you explained the 4 types of treatment in the magnesium. One is the open ladle treatment, that is very much inefficient, and the sandwich method. Third one, the tundish cover with the ladle, and fourth is the wire treatment. We are having both the sandwich and tundish ladle cover treatment we have experienced. According to you, the tundish cover ladle treatment is much giving much good results than sandwich method, because in the sandwich method the cover of the ladle will not be available. And fourth one is, sir, I want to get your what do you say, ideas and suggestions for in-mold treatment.
I can tell you that, let's say, the sandwich method ladle, that's the only one you can use when you have castings above 10 ton. Because above 10 ton, you need such a big ladle, and there is so much metal in it that the sandwich is the most common method and nearly the only one. With a wire in a ladle of 10, 15 tons, you cannot treat the metal properly, because that small wire treats the metal around it, but the diameter is so big and the amount of metal is so big that it's not possible. So, but if you come to smaller, less than 5 ton, then let's say the tundish cover has been proven that it's very, very efficient concerning that. Then go the wire. You have to pay attention that a small wire in a big diameter ladle is not giving the good result. Whatever your supplier will tell you about that, then you need a double wire system or whatever to have the good result there. The advantage of the wire is that sometimes you can also put an inoculation wire in the system, and directly after the magnesium treatment, you can do the inoculation in there. That's a very, very good system. The mold system I have never used. Why? You have such a low magnesium content, and what you have ferrosilicon magnesium. So you add a lot of silicon then by the magnesium, by the ferrosilicon magnesium in your mold. That means by adding that much silicon, the metal in your furnace must have a very, very, very low silicon content. And melting the iron with a very, very low silicon content is very, very difficult. It's very difficult.
And one more thing, staff, when you have the in-mold process, the castings have got high silicon, so the amount of returns that you can use in the subsequent processes also reduces when the returns of in-mold process castings are used.
For sure, for sure. You cannot use nearly no returns then, because the silicon content must be so low that you cannot melt them again. And not melting your returns is a big loss for a foundry. Yeah?
And if you don't remove the slag by the good gating system in the in-mold process, your castings are likely to have slag defects. I have used this process in one foundry for making small castings of weight 2.5 to 3 kilos, two castings per mold. It ran for about 2 years, and then there was so much of buildup of returns that we had to sell the returns as.
Comparingly, all these processes, sandwich method is more generating more pollution, because.
Well, I think I would go to the tundish method, more efficient if you're using consistently large quantities of metal less than 5 tons.
No, sir. If that tundish cover ladle will be D equal to L2, 2 times of.
Yes.
Correct, no, sir. Because
Yes.
if diameter is 1, height of the ladle will be 2.
Yeah, more than 2.
Okay. If
for all ladles, for all types of ladles.
Yeah, one doubt what I'm raising. If the ladle size is too high means it is D equal to 2L, then only that ladle can be used for treatment. It cannot be used for the pouring.
Yes, this is right.
Correct. Then if I go for that tundish, then how I'm not getting the imagination that every time the tundish has to be taken out and kept on the floor, or it is the attachment to the ladle.
No, after the tundish ladle treatment is over, you transfer the metal into the pouring ladle. You cannot pour from the tundish ladle.
That is true, sir. The tundish cover, what I am keeping on the ladle, It will be along with the saddle itself.
Sorry to interrupt you. What's your good name from Gadge Patil?
Jagdish Joshi, sir.
Mr. Jagdish Joshi, there are a number of options available. You can remove the tundish cover completely, as well as you are from Kolhapur. Kolhapur Kelsons is also making some ladle, this tundish cover ladle, where cover remains attached to the ladle itself. So every time you don't have to remove the cover and transfer the metal to the pouring ladle. So that is available. So after this thing, I can send you the different types of tundish cover which are available in the market.
May I know your good name, please, sir?
I'm Amish Panchal from Kastwel. Okay, sir. Now we go to the another question. Mr. Jitendra Shiani is asking, when the tensile test bar is break, the appearance of breaking surface is half white and half black. What is the reason behind this?
Mr. Bazutkar, can you start answering?
Yeah, okay. Well, when you break the tensile bar and look at the fractured surface, the fractured surface reflects light. It depends upon the matrix which is present in the tensile bar, ferritic matrix or polyethylene matrix or a combined matrix. The combined matrix will give you black and white fracture. The ferritic matrix will give you white fracture, and polyethylene matrix will give you black fracture.
Many times when you have problems with a tensile test, please look first if you have no dross in your tensile bar, because dross is very, very frequently present all over. And if you have some dross in your tensile bar, elongation will lower very, very quickly and tensile a little bit. And the dross you can see in a color difference. Mostly there is a color difference then, because dross is not always at the surface. Dross can also be in the section. And dross is coming due to a too high free magnesium content. I can repeat it again. Free magnesium, that's the magnesium from the spectrometer minus 0.76 times the sulfur content, the final sulfur content, should be around 0.028 to 0.035 maximum.
The next question is from Mr. Mohan Raj. Why are you not considered cold wire treatment as more controlled and cost-effective process? Because in India now a trend is lot of foundries are moving from ferrosilicon magnesium treatment process to cold wire treatment process. Yeah, so Mr. Mohan Raj, if you can unmute yourself and if you can share your experience, if you are having, then it will be benefit for the foundry man.
First of the disadvantages, people are using it to make the process more consistent. But like staff mentioned in the slides, it's a costly process. People are going for it. It requires at least 2 wires, one for magnesium treatment and for inoculation. And since the amount of magnesium in the wire is on the higher side, more than 50%, the inoculation has to be also very effective, and large amount of inoculation is required. But yes, people are going for the treatment. Most of the cost involved is in the cost of the mechanism used for feeding the wire into the treatment ladle. That's some kind of a welding wire feeding mechanism which is attached for the magnesium wire treatment. That is why, it makes the process very easy. It is not dependent on the operators. That is most important. And you get consistent results. But that is only if you are making a particular type of.
Mr. Ramavarapu has asked H equal to 2D. Is it a ladle dimension or metal which is treated is 2D? Please clarify.
Is the dimension of the inside of the lining.
2D should be the height of the ladle, or it should be the metal height in the ladle.
D is the average diameter of the ladle height, okay? And yes. 2D is the height of the inside lining after the ladle is lined with the outer shell, with the insulating blanket, with the refractory thickness, and then the height should be measured.
One named Mr. RP has asked, if casting is cold, what will be the cause of degeneration of cold box core with Foseco graphite GNX water base? Grade is 500/7.
I missed the question of Amish. He said, if you're using cold box process core.
It is said that it is a cold casting what is the degeneration of cause of degeneration of the cold box core with Foseco graphite GNX water-based paint and 500 by 7 grade is the metal.
No, 500 by 7 grade of metal, and there is no bad effect of cold box process cores on SGI and the graphite structure unless there's something wrong in the coating.
Core is degenerated. That is what he's saying. Core is degeneration.
Core degeneration.
Yes, Mr. RP, can you unmute yourself and explain to Dr. Basutkar? You can speak in Hindi.
Yeah.
That is also absolutely no problem. Yeah.
Yeah. May I audible?
Yeah,
Yes,
you're
sir.
audible. Go ahead.
Yeah, good afternoon, Mr. Basutkar. It's Ranjit here. May Mr. Staff and you remember me.
Yes.
I had some experience recently. Like I have a casting of 500 by 7 ductile iron casting in which casting is reverse draft, so we have to use a outside core and an inside core for a center core, and we are pouring it through the center core from the bore of the casting, and both cores are painted with the graphite base GNX Foseco paint. So my specific question is, how much a core quality, or I know it's definitely it is affecting, but what should I look like into the core quality or in the core additives for degenerating graphites or chunky graphites get generated in the section? Because from when I'm pouring from the riser ingate is from the inside of the core of the casting, it is remaining prolongated hot for a period to feed the casting, because the outer thickness is where we cannot place the ingates or risers. So how much in that case core quality or core ingredients I have to look for? Because I think we can get sulfur or these kind of those can, and oxidation can be picked up from the core also.
Ranjit, I've understood the problem a little bit. First thing is, the temperature is high and the metal weight that is to be poured into the mold is also high. Then maybe you can give 2 layers of coatings on the core. The first layer is a zircon coating, and the second layer is a graphite coating. And when you're using the graphite coating, make sure the graphite coating is made out of high purity graphite and does not contain any subversive elements. The chunky graphite which you see in the casting is probably due to higher cerium content. I do not know what is the section thickness of the casting. We have given you a table towards the end in which, depending upon the wall thickness, the recommended level of free cerium is indicated in the table. So if you can keep the cerium low or use for ferrosilicon magnesium treatment half ferrosilicon without cerium and half ferrosilicon with rare earth cerium. That will keep the total cerium in the casting low and therefore avoid the formation of chunky graphite. Chunky graphite is only caused by presence of high cerium and high silicon. Take a look at both of these elements and consider, if the core is crumbling or something, consider giving 2 coatings. The first coating of zircon covered by the second coating of graphite. The coating which comes in contact with the metal should be graphite coating.
I have done some trials.
Yeah, get back to me. We can speak about it.
Yeah, sure, sir. Thank you.